All right, y'all ready? All right, so we went over the nitrogen cycle. Do y'all remember what the fate of nitrogen is in the environment? What is the fate of nitrogen? Plant uptake, right in the center. What else? I told y'all there were 3 of them that happen in all the cycles. Which one? Mineralization. Immobilization. So those 3 in just about every cycle that we're going to go over. All right, what else? What about from the atmosphere? Fixation, is that microbes? Soybean, legumes? Okay, so we got fixation. What else? It can be volatilized. Huh?
Leaching.
But how does it leach then? Why does it leach? It has to undergo a process to be leachable. Nitrification. And why does nitrate leach?
Because it's got a negative charge.
What's the overall charge on soils?
Negative.
So a negative do not attract to each other, right? So anions don't hold on to negative charges. What else are we missing? Are we missing something else? I think there might be one more. What did we say? We had immobilization, plant uptake, mineralization, all these fuzzies in my face. What else? We had volatilization, nitrification, leaching. Then we got 2 more. What's that? Denitrification. Some people say it differently. I've heard that term before. Don't. It's okay if you say denitrification, but it's denitrifying. So it has to go to nitrate in order to be denitrified. And then I think we're missing one more.
2-to-1 clay fixation.
2-to-1 clay fixation. Very well, very good. So remember when those clay layers expand, and so which plant available form would you expect to be adsorbed in the middle of those 2 clay layers? Ammonium, and why? So it has the positive charge, so we wouldn't expect nitrate to be fixed in those 2-to-1 clay layers. Very good. All right, so we're going to move into sulfur, and sulfur and nitrogen are very similar. As we mentioned before, in nitrogen, as part of those amino acids, so as part of that aminization, which is part of ammonification. And so sulfur has the same kind of characteristics, and we need these for these amino acids. This is important, probably more so in animal feed and grasses. That's kind of where they get their nutrients from. So if we have low sulfur in our plants, then the animals are not taking it up, and so then they have these issues because they cannot make the amino acids that are necessary for their bodies to perform the functions that they need to perform. That didn't change. Does it say relatively immobile on your sheets? It should say relatively mobile, much like nitrogen. And you might see that in the older leaves. So I'm going to go ahead and change that now. I don't have that problem. You'll see that in the older leaves first. And you would expect to see that primarily as interveinal chlorosis. Right here. So you can see this yellowing of those veins. That's going to be one of the key indicators of sulfur deficiency. So I guess something that we might face coming up in the future, and maybe some of your dads and granddads are kind of in this boat, where all of a sudden we're getting these recommendations where we need to apply more sulfur. And granddad goes, I've never had to apply sulfur my whole life. Why? How come I need sulfur now? Well, back in the 90s, we came up with this Clean Air Act because, we were just burning coal however we wanted to burn coal. We didn't care. and all of a sudden we had all this acid rain starting to pop up, and now we got this environmental movement that came by, and now we got these restrictions. And so, as part of this fossil fuel combustion, we had to reduce our sulfur dioxide emissions, that stuff that was coming out the stack. You know, you might see that, that looks like smoke, but it's really just like the vapor from this process. So when we reduce our sulfur dioxide emissions, we don't get the deposition from the acid rain. So we never really noticed it before because we were getting these additions of sulfur every time it rained. And so going back to kind of thinking about rainfall and deposition, back in the 90s, we had very nice, evenly distributed rainfall. Like it rained every so often, whatever. We didn't have these big storms, these 9-inch gully washers. But if the sulfur is in the rain, and it rains on the field, and the water doesn't go in the soil, where does the sulfur go?
Runs off.
It runs off with the rest of the water. So now not only are we reducing the amount of sulfur in the rainfall, we're also not getting that rainfall in the soil, and so that is depleting our sulfur content because we're removing that crop, especially a hay crop, right? Because each cutting is taking up a certain amount of nutrients and it needs more in order to grow. So coming down the pipe, you might see where we're using like an ammonium sulfate. That S on the bag is going to tell you that there is what percentage of sulfur in this, what's the sulfur percentage in ammonium sulfate? 24%, right? So just like the nitrogen, it's 21%. So when you see the S or you see any other nutrient, that number tells you what the percentage is. That's why we've been doing those fertilizer calculations. And so if you apply 100 pounds of ammonium sulfate, how many pounds of sulfur did you apply? 24. So that's the purpose of me asking you, the soil test recommends blah, 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 blah pounds of nitrogen. How many pounds of K2O did you actually apply? Well, because when you go to do the calculation like this, you can say, I actually applied 24 pounds of sulfur also. And because we're increasing our crop harvest, especially in hay fields and corn crops and things of that nature that require this sulfur, we're removing it from the soil and not adding it back. And we don't get the addition from the salt from the acid rain. So there's no inputs anymore, but lots of outputs. Not that you really need to know too much about like the organic matter and the carbon bond and the ester bond, but there are two different types. That's more like soil chemistry and how those bonds break and organic and rings and stuff and whatnot. But just to understand that it's not the same type of sulfur, especially the organic. And then we have these different bacteria and fungi and microbes. So that's why those microbes were important in Module 3. In Module 3, because these microbes are what break down that fulvic acid that contains this sulfur, or this carbon bonded or ester bonded sulfur molecule, some protein, some amine. We need those microbes to decompose that structure, which then releases the sulfur into the soil. So some of the factors that are going to affect soil adsorption is going to be kind of like this is where pH dependent charge comes into play. And the different types of soil where we might have a greater adsorption in like kaolinite. We would also have greater adsorption in acidic soils. So when we add lime, what happens to the pH? It goes up. When the pH goes up, what happens to the CEC? The CEC goes down. it goes up, right? pH dependent charge. pH goes up, CEC goes up. Which one's more positive?
It's less rises, the negative charge.
The negative charge rises,
It's
right?
still negative, but it's less negative.
The functional groups of organic matter dissociate a hydrogen, leaving the negative charge. pH goes up, CEC goes up. When the pH goes up, what happens to the AEC? It goes down. And sulfate is an anion or a cation. 50-50. It's an anion. And so if the AEC goes down, are we going to be holding more sulfur in our soils at high pHs? No. But as the pH goes down, what happens to the CEC?
The pH goes down.
pH goes down.
What happens to the CEC? Is that what you said?
Yeah, what happens to the CEC?
It goes up.
The CEC goes down.
Yeah.
The AEC goes up. And since sulfate is an anion, in acidic soils, we would hold on to more sulfate. More organic matter, we have this pH dependent charge. It's going to adsorb some of that. And then oxidation state. And this is something that we talk about more in like fertility or some environmental chemistry where we're changing oxidation states. We talked about this wet deposition from acid rain. We can also get some dry deposition, and so in order to minimize this, the sulfur coming out of the stack, they use like a liming material because it will adsorb to the lime, and some of that does leak out of that stack. So kind of from top to bottom, we have deposition and plant uptake. Remember, plant uptake is going to be central to all of our cycles. We will have some immobilization and mineralization. Very small amount of volatilization, very, very minute compared to nitrogen. It can be adsorbed to the AEC, and since it's an anion, much like nitrate, it can be leached. Everyone pretty good right here because we're about to do the cycle part, which is going to fill all the rest of this in. All right, deposition from the atmosphere. We're also going to apply some ammonium sulfate, some other fertilizers, but we're going to get a little bit from deposition that starts the cycle. I'm just going to kind of go in order the way that from top to bottom. So we have deposition. Once it's in the soil, it can be taken up by the plant if it's been converted to a plant available form, which is sulfate. There are some processes that go on where the sulfate can be volatilized under the right conditions. We have to kind of more reduced conditions where we're losing some of those oxygens and that sulfate becomes a sulfide that is in a gaseous form. Everyone good? Next, everyone's favorite, immobilization and mineralization. And this is the conversion of this sulfide to elemental sulfur. And elemental sulfur is one way that you can take your pH from alkaline, say pH 7.5 to 8, back down to about 6. You can apply sulfur or you can apply aluminum, soil chemical properties. But just for a little bit of knowledge, in case you ever get your soil test back and go, oh, we have a problem because our pH is too high and this is why our crops won't grow, you can maybe apply elemental sulfur or aluminum to solve that issue. We have sulfate adsorbed to the AEC. And then finally, it can be leached out of the system into the groundwater. Not nearly as much of a problem as nitrates and nitrites, but you know, we really don't want stuff just leaching into our groundwater. We prefer to have that as clean as possible. So now we have to figure out this balance between keeping our pH at the right level so that our nutrients are available, and also that our AEC is high enough that we can hold on to this sulfate so the plants can take it up. So our plants almost kind of act like the last defense from the leaching down the soil. If we can get the plants to take it up, it doesn't have the opportunity to leach through the soil profile. Good here? All right, so now you've done the nitrogen cycle and you've done the sulfur cycle, but they're more intricate in the nitrogen cycle, and that's why we started off with the hard one, because the rest of them are just going to be easy. They won't be nearly as hard. But we have some movement from the atmosphere into the soil. We're going to have immobilization and mineralization, plant uptake, leaching, and sun release back into the atmosphere. That's like in the nutshell of what's going to happen in most of these cycles, especially the nitrogen and the sulfur. From the atmosphere, immobilization, mineralization, plant uptake, leaching, some volatilization. But a big difference in the intricacies of them. Next is going to be phosphorus. I guess maybe y'all might be close enough to plant science. Do y'all remember doing like photosynthesis and the Calvin-Benson cycle and respiration and the Krebs cycle? Some kind of. I have to throw that out there and refresh some of that memory. But anyhow, ATP, so when we do this process, and humans do this as well, you know, we need that phosphorus as an energy source. Phosphorus is loaded with energy based on its chemical makeup, like because phosphorus is what it is. All those electrons orbiting and all the bonds that can form, and now we're back to chemistry and it's essential in DNA and RNA. So we have photosynthesis. Phosphorus is important for flowering, fruiting, and seed production. And this is also going to give us, like right here for this prevents lodging. You remember for nitrogen, if we apply too much, then that plant can grow too fast and not have enough strength, and it will be spindly and weak and it will fall over. So we get enough balance between nitrogen and phosphorus, and we can kind of start to build some structure in our cells. So phosphorus is important in those cellular membrane, wherever that's at, cellular membrane. So if the cell structure is rigid and kind of solid, then we can build on that and our plants stand up a little bit better. Phosphorus is one of the easiest deficiencies to recognize. This purpling effect, has anybody seen this? Brandon? You seem to be the guy that's got kind of sort of, y'all see this in beans? No? Right, because y'all apply the right amount of fertilizer. But, you know, kind of in the beginning of the year, maybe for corn, we're planting this corn, it gets up and then it gets kind of cold. The phosphorus is immobile in the soil and the plant can't take it up, so. But it's in our chicken litter, right? So when we apply that organic matter, that organic fertilizer source, it has to undergo immobilization or mineralization. Pick one. Huh? Now it is mineralization. Organic to inorganic. Immobilization is inorganic back to organic. Our biggest problem with this phosphorus is that it's adsorbed to our soil so tightly. It's one of the strongest plant nutrients that is adsorbed to the soil. And so when we have runoff and erosion, that's how the phosphorus gets in the streams. Is there anything on this? I'm trying to kind of rush through this because we're trying to get to a good stopping point for the quiz. Maybe. Again, that runoff and that erosion is going to cause that downstream eutrophication. And when I was making this slide, y'all look at this right here. That 10,000 beef cattle produced the same amount of waste as Murfreesboro. So 10 times the amount. And they cause these algal blooms and this hysteria, and cyanide is a gas that will kill you. So we have these things in our waterways, and they're causing us some problems, and we really don't have a solution for fixing it. Our only solution is to try to prevent it. So having an understanding of how to prevent your soil from eroding off of your land that has the phosphorus that you spent all the money on that your plants need is going to be important. So we have two plant available forms of this phosphorus that has several different chemical compositions, but the two that the plants can take up are going to be H2PO4 negative and HPO4 2 negative. And so this is probably about as much chemistry as I try to bring into this class, but we've talked about some about pH, and so if our pH is 4.5, what would you expect the hydrogen concentration to be? High or low? It's 50-50.
Probably high.
It's probably high. It's correct. pH. So the more hydrogen, the lower the pH. Y'all look at this H2PO4 negative. That's kind of the indicator that if your soil is acidic, so we have a high hydrogen concentration. Let's see if I can pull the marker. All right. So here we are with I'll show you all this backwards. So the greater the hydrogen concentration, one of these oxygens is going to give up some charge. and we will get another hydrogen. So the more hydrogens there are in the molecule. Acidic soils, high hydrogen concentration, H2PO4. So the opposite goes for if we have a high pH, what do you expect the hydroxyl concentration to be? Higher. So now we have it back the other way.
So they can duplicate,
What's that?
they can duplicate and get bigger. Just keep growing.
What
You took the hydrogen, made it into hydrogen two, phosphorus four.
right?
So they can duplicate off itself, or you lose a hydrogen.
So you would lose a hydrogen the other way. So if we have this OH negative, much like and we have H2PO4 negative, one of these hydrogens will dissociate. That will form water, and then that charge will change. So that's where setting up that pH dependent charge and that whole concept of equilibrium and dissociation depending on the pH comes into play. So if you have a low pH and a high hydrogen concentration, we can expect it to be H2PO4. If we have a high hydroxyl concentration, one of those hydrogens will dissociate off. And then this sweet spot, the equilibrium where we have 50% H2PO4 and 50% HPO42 is right here at about 7.2. Right, so there's this change that's going to happen as we have this pH influx, and we're going to change our speciation for phosphorus. 7.2 is the equilibrium between H2PO4 and HPO42 negative. So you can start to begin to think about which side of that 7.2 you fall on based on your soil test. So you'll know which plant available form you're taking up. All right, here we go with another P cycle. A little bit different than the other two that we had, because our only inputs are going to be from fertilizers and residues. So we don't have any atmospheric deposition. We don't have any outside sources bringing this in other than humans applying fertilizer, or maybe some biosolid, some bovine biosolid byproduct. You know what that you know what that is, Brandon? Take a guess. What's bovine? A cow or a bull, right? And then the biosolid byproduct, what's that? Yeah. So we have some bovine biosolid byproduct or some other animal manure that we apply to this fertilizer. The three that are in every cycle is going to be plant uptake, immobilization, and mineralization. And immobilization is which way? Right, but like which form? Organic, inorganic, what's the conversion for it? It's converting an inorganic to organic, immobilization, inorganic. And so that would mean that mineralization is which? Organic to inorganic. So they're equilibrium based on the needs of the microbes. So we have the P that is adsorbed to the soil with a D. Adsorbed. So there's this adsorption and desorption process. This would actually be anion exchange. adsorb to the soil, desorb to the soil. And there are a couple of things that influence that, but for the most part, just to understand that it's adsorbed. It can form secondary primary minerals. And so this is going to be something that's going to require it to be dissolved. So there would be some solution or some breakdown of some mineral that caused a reaction that would change the pH of the solution that's right near this phosphorus particle, secondary mineral, that would require it to be dissolved in order to go back to H2PO4 negative. And then finally we have those primary P minerals, typically going to be like calcium phosphates of some sort. Just to know that it can either be adsorbed, it will form a secondary mineral, or that it will form a primary mineral. And then finally, either runoff and erosion or crop removal. Well, did y'all need that still? So these cycles will probably be on the final, there's no probably, they will be on the final exam. And I've posted the practice so that you can print these off and get practice filling them in and memorizing which one goes in which block. When we get to fertility, it'll be a little more in depth and you'll have to go throughout explaining it. But you should be aware that this is the reason why we're in soils class, is to understand our fertilizer, and that's going to be ag business, and kind of this is going to cut into our budget. We need to make sure that Stephen knows what he's doing and running the budget. And that's why you hired them, right? Because they do know the budget. And
Oh, yeah.
you know the field, they know the office, and that works well. Kind of the most important thing is that you won't find any volatilization in the phosphorus cycle. So it's not like an atmospheric and a water problem like nitrogen. Nitrogen is an atmospheric and a water problem. Phosphorus is not going to volatilize. It doesn't form a gas. Those aren't anything. So do y'all remember for carbon to nitrogen what the ideal microbial diet was? 24 to 1. And so in nitrogen, if we get below 20 to 1, we would have a net mineralization or immobilization. 50-50.
Immobilization, if you do,
Below 20 to 1.
so mineralization.
A mineralization, because now there's more nitrogen in that,
Yeah.
or there's less carbon, but the ratio is higher. So phosphorus has one. The microbes still need that phosphorus, because remember back in that ATP, part of those cycles, that's where they get their energy from, for their cellular functions. And we're going to find most of these high P fixation in altasols and oxasols. And so if y'all can remember back, these are going to be our highly weathered soils. So there's nothing left but the central molecule of that tetrahedron or that octahedron. So it's either going to be like aluminum or aluminum or magnesium, possibly silica, but it doesn't really have an attraction for that. But aluminum and magnesium for sure. In our volsols and vertisols, acid soils, low solubility, alkaline, high solubility. I think this is more just for some information in case you ever run across this and kind of go, how come we put all this phosphorus out and we didn't get it and we still see the purple? What's your soil type? I'm gonna go to Web Soil Survey and pull this field up and go, oh, look, you have an oxisol or an ultisol, that's why. And so here's the thing about applying phosphorus fertilizers. The longer the P is in the soil, the less the plants are able to take it up, because it's a diffusion gradient. And so you don't want to apply phosphorus because it will force the plants to change the environment and uptake that P. So the more P you put out, the less is available. And so here we are putting out triple 13, we're putting out chicken litter that's like a 3-3-3, but we're putting it out at a ton per acre, and it's got 60 pounds of phosphorus, and we're doing this every year. So if it's not, the soil can only hold so much phosphorus, and if it doesn't hold the phosphorus, where does it go? Into the ditch. So something to figure out, something to be thinking about. Like in Florida, you can't get any phosphorus fertilizer because they have enough already. That's where they get the phosphorus from, is actually Florida. You'll start to see a 13013. If you go to Lowe's, you won't find very high phosphorus content fertilizers. A couple of the types of fertilizer that you might run are phosphorus compounds is going to be apatite. So this is what they mine in Florida. They mine the apatite, and it has to undergo these chemical processes so that we can get it into triple 13, or we can get it into DAP or MAP, so that when it gets into the soil, it releases in a certain way that creates those plant available compounds.
What is the ammonium phosphate? What is that in fertilizer?
The what now?
Like the DAP.
DAP?
Ammonium phosphate.
Diammonium phosphate.
Yeah. What's the diammonium?
There's 2 ammonium molecules for each one of those HPO42 molecules.
Okay.
So it has to balance.
Right.
Right. So the charge on ammonium is
Negative.
on ammonium positive. But positive what number?
1.
Positive 1. And the charge on HPO42 negative is negative 2. So we need 2 ammoniums to balance out the HPO42 negative.
Okay.
And when you add that onto your soil and we get water, it splits those two, and now we have a plant available P and a plant available ammonium. That's how that chemistry works, and so you have to have those two together. When it dissolves,
To get that.
now you get 2,
2 different.
yeah, there's 2 ammonium molecules in that diammonium phosphate. And so monoammonium phosphate would be 1. All right, that's
It's
cool.
confusing.
No, I know, no, but it's not. It takes a moment to think through it. It's not confusing. We have NH 4+2 and HPO4. I want y'all to think about this for a moment. Before this gets combined, this is 2 negative, right? So we have ammonium and we have phosphate, this HPO42 negative, which you would find in which soil type? pH, higher or left? Which one?
1.
How many hydrogens do you see in that molecule?
Or in that 1 molecule?
In the HPO42 negative? 1.
Okay.
So, right. So these 2 ammoniums, let's just maybe we do this like this. Right? That's what this molecule would look like. See this here? So we got H2PO4 negative that only gets balanced out by 1 nitrogen. So now that we know this, we can say which are we applying? Which plant available form are we going to apply when we apply DAP? HPO42 negative. which one when we apply MAP? H2PO4 negative. Right? That's about as chemistry as we really need to be. Just positives and negatives is all chemistry is.
Let's just remember which one's which.
It's just remembering which one's which. That's absolutely correct. All right, and so we have these iron and aluminum hydroxyphosphates. And so what are the three sources of pH dependent charge? You got one for me, Sydney? Any one of them. Now that's a long ways ago, brother. That was back in module 2. But I saw the light bulb go off. You heard it and you were like, broken edges of clays. Guess what's going to be on the final exam? Aluminum and iron oxides, and we got one more.
Yeah.
The functional groups of organic matter. That's where all this stuff comes into play. So we have these aluminum and iron oxyhydroxides. So it would help to know iron and aluminum on the periodic table. But also I want y'all to think about something. Look at all the E's in strontium. And it is the iron phosphate. Now look at variscite. The A in variscite equals aluminum phosphate. Yo, when I was like a master's student, I put that together by myself. I was telling everyone about that. I was like, hey, y'all, check this out. Look at this. Look, I came up with it. I figured out how to get over this question because the person who taught soils was just cruel. He did not suffer fools, man, at all. So when I found this out, I was like, got it. I got it. It's right here. So those are some good ways that you can possibly remember some of those things. I really just kind of put this in here just in case if, for those of you who like all those positives and negative charges, because there are a few of us out here who enjoy looking at anions and cations. If you move further and you decide to get into soils, some of these are going to be important for fertility. There it is. H2PO4 negative attracted to the positive charges of aluminum and iron oxides and broken edges of clays. They're going to form these outer sphere complexes. This is more of a soil chemistry type thing, but I guess the best way that we could describe that is that when the phosphate is adsorbed to the soil, it is adsorbed like this. It's like a magnet type deal. There's some water in between there, and that forces this little magnet. Attraction, chemistry. I see some people glazed over. They're done with chemistry. But when we have an inner sphere complex, it is actually like more adsorbed, like a covalent bond. So now we have a block like this. Inner sphere complexes are more difficult to break because it's a covalent bond. This outer sphere complex is more just like a piece of tape or a magnet. Like that's cation exchange or anion exchange simply. Is all that really is. Organic matter is going to influence replacing those phosphates as well. I think we're good there. That should get you enough to complete the quiz that was uploaded. That should be available today. That quiz is due Friday. So up to about right here in this area is everything you need for the quiz. All right. Cool.
Would you go back like 4 slots?
Sure. Which one? This one? Cool. All right, that's it. I forgot to get business card for you, Stephen.
Yeah.
I don't. I mean, I have it in my office, but I know you said
Yeah.
I have like my tech business cards, but I need to get like my business card.
I mean, I think it's a good idea, so, because, I mean, as much as I'd like to be an expert in this, I don't need to be an expert.
No, you're right, you're managing, someone else will subcontract that out. That's
Exactly,
fine.
exactly.
As long as it fits inside your budget, so like, you have to think about that as well.
What's gonna be the capital return on this?
Like, that's my problem. That's my problem. I come in and say, if you let me come out and sample your soil samples for $25 a sample over blah, blah, blah acres, we expect you to get a net profit of $7 an acre. Is that worth it to you? I don't know yet. I don't know if that's,
You know, when you stretch it over a large amount of acres,
then it is, right.
be able to learn exactly what you're doing, instead of just assuming. Because I've learned there's a lot of assuming.
What's up, Larry?
Got a little situation for you.
Okay. I don't care.
Come to check the lab.
Whatever you need to get registered for class, whatever you do for that, right?
Well, I was gonna come to you. I got everything set, saved in my car, but I know I got some of it in 5-15 minutes, dead or alive, time, I know what you would say, right?
I would much rather you get registered for class and
I'll be at lab at around 5 o'clock, I'm gonna quit, I hate to watch this.
then, you know, we don't stay till 5:15 anyhow.
I appreciate it.
Yeah, man, you're good.
I gotta get my classes scheduled for the fall. I want them summer classes. I like them summer classes, I get time off quick, absolutely no way.
There's no way I'd come in person. I couldn't do that.
No, man, you take all that crap online. You take all your like literatures and your modern histories and all that garbage online. So I did.
I've already got all those
Oh, okay.
out of the way
See,
at a community college.
We got people waiting for us.
time.
Hmm?